Hello students. So in this video we are going to discuss flat top PAM wave. How we are generating flat top PAM signal. Okay. So this is your sample and hold circuit. It consists of two FETs, okay, and one capacitor. So we are applying the modulating signal at the input of our FET 1. So along with that, we are applying the small pulse for the small duration at the G1, gate 1, right? We have three terminals for the FET, right? Source, gate and drain. So we are applying the small pulse at the gate. So what happens? The FET is closed. Once the FET is closed, the capacitor start to charge. It capacitor charges up to the maximum value of our input signal, modulating signal. We will discuss by using this waveform. This dotted line indicates our modulating signal, X of t, our input signal. This rectangular square wave is our PAM, flat top PAM signal. Why we call this one as a flat top signal? Because our PAM output varies according to our modulating signal, right? But this amplitude at the top, at the top, the amplitude is constant. It is not varying according to our input signal. It is constant. It is constant for the fixed duration, right? So we call this one as a flat. This is flat. It is present at the top. That's why it's called flat top PAM signal, right? So once if you are applying the small pulse uh, at the gate of FET 1, so the FET is closed. Once the FET is closed, the capacitor start to charge. It will charge up to its maximum value of our input signal, right? Up to this one, the capacitors start to charge. After that, what happens? So the FET 1 is open. After the short duration, right? After certain duration, right? After certain duration, the FET 1 is opened. So open means what? The capacitor holds the charge. Capacitor holds the charge for some duration. We call this one as a tau. Okay. After the capacitor holds the charge, the FET to 2 we are as soon as if you are applying the short pulse, right, at the input of G2 of FET 2, so the FET to 2 is now becomes closed, right? So G1 that FET to 1 is opened, FET to 2 is closed. So once the FET is closed, the capacitor start to discharge towards the FET to 2, right? So now the capacitor discharges slowly at the FET to 2. So in this way, opening and closing of FET 1 and FET 2, so the capacitor charge and discharge, right? So here the FET 1 we call this one as a charging switch. We can also call this one as a sampling switch. The FET 1 is a charging switch, FET 2 is a discharging switch. So based on our input signal, where we are applying at the G1 and G2, the capacitor charge and discharge. So based on the charging and discharging of capacitor, we will get the pulse. So we will get the pulse. It is a sequential rectangular pulse. It is, see here the my height of this rectangular pulse is high when compared to the initial value of our modulating signal. Why it is? Because as the amplitude goes on increasing, the height of the rectangular pulse is also increases. Here my modulating signal amplitude is very low. That's why I'm getting this. The height of the rectangular pulse is not that much good enough when compared to this one. It is very low, right? The height is low, minimum, right? When compared to this rectangular pulse. Why this here the rectangular pulse is bigger than this one? Because my maximum amplitude of input signal is high. That's why we are getting a maximum height of rectangular pulse. So in this way, so we are generating the flat top PAM signal, right? So we will discuss what is aperture effect. So you will get for 2 marks, define aperture effect. So usually in the flat top sampling, right? So to convert varying amplitude of pulses, right? So actually the aperture effect it exists, it occurs during the flat top sampling, right? I have discussed what is the flat top sampling and natural sampling while discussing the different types of sampling method or different types of sampling technique, right? So during this time, right, so in the flat top sampling we need to convert varying amplitude of pulses, right? So that's why we call that one as a flat top PAM signal, pulse amplitude modulated signal. So during that time, so we need to we need to perform convolution, right? So with the h of t. So I have written one equation, right? X delta of t, x delta of t should be convolved with h of t. This h of t is the Pearl string, right? Pearl string. It is a rectangular Pearl string. So in the frequency domain, we are representing as a sinc function, right? So once if you are performing the convolution operation with the x delta of t, so what happens? It decreases our amplitude. Why we are doing this one? In order to get flat top PAM signal, we need to perform this operations. So because of this h of t, so in frequency domain we call this one as a sinc function. So we will get the decreased amplitude in the PAM signal. We call this one as a aperture effect, right? So it will obtain during generating the flat top PAM signal. Okay, decreased amplitude because of sinc function, right? Because of sinc function, we are generating a decreased amplitude of flat top PAM signal is called aperture effect. Now we will discuss how we are detecting the flat top PAM signal. Now, before that, we have discussed how to generate PAM signal. How to generate PAM signal. We have discussed by using a sample and hold circuit. So this is our sample and hold circuit, right? So by using this sample and hold circuit, we have generated flat top PAM signal. So during generating, aperture effect exist. So then we are generating this PAM signal at the transmitter side. At the receiver side, what we should have to do? I have to get original signal, which means I need original modulating signal, right? So now I have to detect my modulating signal from the flat top PAM signal. So for this one, so we are using this circuit. So we are giving this PAM signal with noise. We are giving PAM signal with noise to the reconstruction filter. Okay. So in the reconstruction filter, we have the low pass filter. So what it will do? It will remove high frequency electrical signals. It removes high frequency signals, electromagnetic signals, right? It removes high frequency electromagnetic signals, which is our unwanted signal. It is a noise signal, right? So after that we will get the PAM signal by removing the noise. And but during generating, so it we will get the decreased PAM signal because of aperture effect. But I need original modulating signal at the output side, at the receiver side. So in order to get, so we have to send this to the equalizer. We have to send this one to the equalizer, right? So here equalizer is used to, first one is in order to remove aperture effect, and also in order to equalize my amplitude of the signal, right? Because of my aperture effect, so it varies the amplitude, right? So I want the original without varying, decreasing amplitude signal. I need exact amplitude of my original signal at the receiver side. So in order to remove aperture effect, we are using the equalizer. One more thing, here we are using the low pass filter in order to get my original signal, right? In order to get my original signal. So, and also in order to remove noise also. So in order to remove noise and in order to get my original signal from the PAM signal, we are using the reconstruction filter. During that time, attenuation occurs. So attenuation means reduction of amplitude, right? So in order to overcome the problem of attenuation and aperture effect, we are using the equalizer. So finally, we will get the message signal, right? So in this way, we can detect modulating signal from the PAM signal using this reconstruction filter. So from the reconstruction filter, we are removing unwanted high frequency signals, and we will get the decreased amplitude of modulating signal. And also in order to remove the aperture effect and attenuation, so we are using the equalizer. Finally, we will get the modulating signal, right? So I hope you have and you are able to understand how we are generating flat top PAM signal, and we are detecting the PAM signal. So in the next class, we will discuss the transmission bandwidth of PAM signal and pulse position and pulse width modulation, right? Thank you.